Hello guys, welcome back to my video lecture series on the derivation of the Black-Scholes European option pricing model. And in this video, we're finally going to reach the point where we establish the Black-Scholes partial differential equation. So before I do that, I'd like to reiterate what we've discussed in the previous video, which is the following. We constructed a portfolio represented as pi. As such, we represented it as one of our financial derivative minus a delta amount of our underlying stock for the financial derivative. And what we did was we found the change in that portfolio as the change in our financial derivative minus a delta amount of the change of our underlying asset. And further, we assign delta as the partial derivative of our financial derivative with respect to our stock. And this is actually a very important option Greek. There are many more option Greeks that do exist, but in this video lecture series, I will not be covering all of them. The only one I will be covering is delta, which essentially tells you how many underlying assets one of your financial derivatives would be represented as. So, for example, if I were to hold a delta amount of the underlying asset as well as one option or one financial derivative using that underlying asset in my portfolio, then I would essentially be risk neutral, right? So if my delta was, for example, 45, then if I held one financial derivative, then I would need 45 of those underlying financial assets shorted to construct a risk-free portfolio. And the way we represented a risk-free portfolio after a mathematical derivation was as follows. We said that d pi is going to be equal to the partial derivative of our financial derivative with respect to time plus the second partial derivative with respect to stock price times volatility squared, s squared over 2, and this is all times dt. So what's good about this is that it is a partial differential equation and not a stochastic partial differential equation, meaning it is not stochastic. There are no stochastic elements, dw or db, so essentially there's no randomness. Now, what we want to do is get rid of this d pi, because what we're interested in is v. We don't need the extra variable pi, because again, what we're interested in is our derivative price. So to do this, we want to construct another risk-free portfolio. So this is going to be a risk-free portfolio using the risk-free rate. And we're going to denote the risk-free rate. I'll write that again. Risk-free rate as R. And R is going to be in percentage form. And you can think of this similar to how we had mu as mean returns and sigma as volatility, also in percentage forms. So that being said, we can deduce that the change in our portfolio with respect to time is going to be our risk-free rate, and because it's in terms of a percentage, we'd have to multiply it with the value of our portfolio. This is in the same way for mean returns, we'd have to multiply it with our stock price, and for volatility, we'd also have to multiply it with our stock price. Same idea, because these are all represented as percentages. And just to make it clear, the risk-free rate is derived by many economic factors and is available on many resources online. It is not a constant, it does change over time, but for the sake of the Black-Scholes derivation, we're going to assume it's a constant. So we're going to assume R is a constant. Now we can rewrite this in the following way. We can say that d pi is equal to R pi dt. And we said that pi is going to be our V minus delta S, a delta amount of S, where our delta is going to be the partial derivative of V with respect to S. Now we can plug this in, and now we'll have d pi is equal to the risk-free rate times V minus the partial derivative of V with respect to our stock price, and that's going to be multiplied by our S, and we're going to multiply that by dt. Essentially, I just replaced my pi with this following representation right here. So this is going to be my pi. Okay, now this is going to be one representation, and again, the second representation we had of d pi is going to be as follows, which we derived in the last video. We said that it's equal to the partial derivative of our financial derivative with respect to time plus squared v ds squared times sigma squared s squared over 2 all times dt. So now we have two representations for the same thing. So obviously we can set them equal to each other. So if I were to do that, I would say on my left-hand side, I would have r v minus the partial derivative of v with respect to s times s, all of that times dt. And on the other side, I would have my partial v, partial t, plus my second partial derivative, times sigma squared s squared over 2, all multiplied by dt. So as can be seen, dt is on both sides, which can be cancelled. And what I'll be left with now is going to be rv minus the partial derivative of v, partial s, rs is equal to dt plus squared v squared sigma squared s squared over 2. And one point that I want to make over here, pi does not exist in this expression. And when we keep going with this derivation, pi still will not exist. So that's what we were trying to do in the first place, so it works out. Cool. Now we can rearrange everything and put 0 on one side. And on the other side, we would have the partial derivative. Actually, I'll do this on the next line, just because it's important. I would have 0 is equal to the partial derivative of my financial derivative with respect to time plus my second partial derivative of my financial derivative with respect to my stock price times my volatility squared times my stock price squared over 2 plus my partial derivative of my financial derivative with respect to my stock price times the risk-free rate times S minus my risk-free rate times my financial derivative price. And that's all going to be equal to 0. And this is what we call the Black-Scholes partial differential equation. Which after 16 videos, we finally derived. Thank you for listening.